Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. So in the previous lessons, we learned about the open loop Ziegler Nichols method and the closed loop Ziegler Nichols method. Now what we are going to do in this lesson is that we would like to apply two examples, one on the open loop and one on the closed loop. So we will start with the open loop. First we will open MATLAB Simulink. So new Simulink model and create a blank model like this. So I'm gonna add first a step function, not a transfer function, okay, like this, and make it for the numerator. We don't have any kind of zeros. For the numerator, it will be a second order system of 8s squared plus 8s plus 10, like this, okay. And then I'm going to use a scope to observe what's happening, and I need a step function like this. Starts as a time equal to 0. Okay, so it starts at time equal to 0, goes from 0 to 1. Okay, and then I'm going to run the system for 10 seconds, like this. If you observe the behavior, it looks like an S shape, a close to S shape, okay? Not exactly an S shape, close to it. Okay, and you can see that the steady state value is 0.1 despite giving an input of 1, right? The input is 1 and the step input here, the output here is 0.1. So it means there is a large error requiring a controller like the PID controller. Okay, so what I'm going to do now in order to apply this formula, we need to get the point of inflection, point which has the maximum slope, and draw a tangent line to it to find L and T and get the PID controller. Okay, so how I'm going to do this? First, I'm going to use a two workspace like this and call this X. Okay, what does this do? It takes this this output function and saves it to workspace in variable called X, or out.x. If I would like to remove this out, it is very easy. All you have to do is go here to settings and then goes to data import and export and remove or untick the single simulation output like this, and then run. And then go to workspace. Here you will find that the variable X here. So I'm gonna plot this like this. Okay, now I would like to get let's zoom in like this. Okay, I would like to find the point at which we will have inflection. You can see that the slope like this and increases and increases and then starts to decrease. So the point of inflection is at this part here. So what I'm going to do is that I'm going to insert. You can see all of this is just an approximation. Okay, so align like this and move it like this, and then move all the way until it intersects here, and move all the way until it intersects here. Okay, now first I would like to find this point, the intersection point here. Now look carefully here, you will find that this point exactly has, and this point above it, this two here above each other, has almost the same x-axis. Okay, Now you will say that I can't get this point exactly. I will tell you why. Because we need to do another thing. We need to go here, edit, in order to make it more accurate. Solver details, fixed step, and choose the step to be 1e to the power negative 4. So it is about 0.1 millisecond. Okay. A small sampling time in order to get more points from the graph, and then run. Then go here and plot x once more. Okay. Then let's look at this graph. Okay. And let's zoom in once more, like this. Okay. And then you'll find this line here. Okay, so I'm going to do it once more, like almost like this. Okay, remember that this method is just an approximate method, depending on how accurate you are going to select the point. Now we want this point here. If I go up here, you will find more points. You can see that we have this gray dot. We have more of this gray dot. So I go up like this and approximately here. So it will, x will be about 0.07. Okay, we can say 0.07. Okay, you can see here distance of L. Now we want the distance of this point here. Okay, now you will say that, remember that this x is similar to this x. They have the same coordinates for the x-axis. They have a different y-axis. Okay, and then I'm going to draw another line like this. Insert another line and go here. I will try to make it more accurate as I can. Now if I would like to make it exactly like this, we can make this like this and this point like this. Okay, so I'm going to move this. So we are exactly looking for this point. Okay, so this point is pretty close to 1.1. so this distance from here to origin is 1.1. so our t will be the difference between this point and this point, similar to this graph. So we have 1.1 here. So t will be difference between L and all of this. So t will be 1.1 minus 0.07 gives us 1.03. Okay, so now we have our values. Now we would like to get the others, which are, we are going to use PID controller. So it will be 1.2 t over L. So I'm going to calculate this on my own calculator. 1.2 multiplied by t, which is 1.03 over 0.07, right? So the gain is approximately 17.65, the proportional gain. And the other one is 2L. So it will be 0.14. Remember that this one is TI. So TI, and we need KP over TI to get the integral gain. So it will be 17.65 divided by 0.14, 126, okay, multiplied by 2L, okay, 2L. This is TI, okay, great. Now for the derivative gain, by applying the same formula, 0.5 of L multiplied by KP, which is 17.65. This gives us 0.61775. Okay, so we have the three gains, P, I, and D. So I'm going to go to MATLAB here. Okay, like this, and then type PID controllers or PID controller like this. Okay, and then I'm going to add the 3 gains, 17.6, which I obtained by substituting, and the integral is 126, derivative is 0.61775. Okay, and then remember this is a closed loop system, so I'm gonna add sum and make the sign negative. Okay, remove this, get back here and get a feedback. So we have a unity feedback system, a closed loop system, and we applied a unit step function after designing the PID control. So let's see the response of the system. You can see that the system reached the steady state of 1. Actually great, so it reaches a steady state of 1. However, there are some oscillations, so we have a starting point, these gains representing a starting point for our system. Then we are going to use these gains, and we can use them in optimization algorithms, as we will explain later in the course, or by using manual tuning inside MATLAB Simulink. Okay, so this is for an open loop system, okay, or not an open loop system, a closed loop system, but with an S-shaped response. So we applied the first method. Now let's look at another example for the closed loop Ziegler Nichols method. Okay, so in this method we make the integral 0, differential gains 0, and we increase the proportional gain until the system is critically stable. Okay, until we have a sustained oscillations like this and we get the frequency or PU, and then we can design our PID controller. Okay, now I'm going to show you how to do this using a hard step and using an easy method. Okay, so our system in this problem will be like this, will be 1 over s multiplied by s plus 2 multiplied by s plus 3. So we have two options, either to type 3 transfer function multiplied by each other, or you will find an easier method, which is a zero pole block. What do you mean by zero pole block? Zero pole continuous like this. You'll see this one. This block in MATLAB Simulink helps you to add zeros and poles as you would like. So I will double click here, and step 1, what is the gain of my system? My system here, which I'm going to apply to it, is has a gain of 1. Okay, how many poles, how many zeros we have? We don't have any zeros. Okay, so I'm keep this empty. 2 empty brackets means we don't have any kind of zeros. Okay, this is different from this block. When you add 1, we will have a constant gain of 1 in the numerator. And this one, when we have an empty brackets, it means that the zero pole, it means we don't have any kind of zeros. Okay, great. What about poles? We have 3 poles. We have 1 at 0, 1 pole at -2, and 1 pole at -3. So if you click on apply, you will have this transfer function, gain of 1. We don't have any kind of zeros here, and we have 3 poles, 1 at the origin, 1 at -2, and 1 at -3. You can see at -2 we have a 0, we have a pole, and at -3 we have another pole. Remember, this formula here, numerator and denominator, is different from this transfer function. Okay, so let's push this here. Okay, like this, and let's put this one here. Let's delete this feedback for now. Delete this. Okay, and this, and take this one here like this, in order to see if I can apply the first method or not. If I run the system like this, you will find here a weird response. So let's make this one 300. Let's see if I can do 300. So you can see that the system is still going up. So we don't have the S shape. It doesn't even reach a steady state response. So what I'm going to do now is that I'm going to use the second method, which is a closed loop method. So I have normally a closed loop as I want, like this. And then instead of PID, I'm going to use only a proportional gain. Remember that the proportional gain affect the root locus, right? So if we increase this gain, we can increase the oscillations in our system until we reach the critical state at which we have a sustained oscillations before the system goes to instability. So you will see that now. Let's start with the gain of 5, okay? And then run the system, open it. You can see we have a normal response reaching to 1, okay? What if I increased this gain to 10? Like this. We don't have the oscillations. Let's make this 120, okay? And you see you're still having you can see oscillations, but they die. So we're still in the stability zone. So let's make this 28, okay? You will see that we have oscillations, more oscillations, but you can see that they are decaying. So it will reach a steady state after a long time. Now if we apply, let's say 35, and look, you can see that the system reached instability. The oscillations are increasing. I don't want this. I want a sustained oscillation, not increasing and not decaying, okay? Okay, so how are we going to do this? Let's decrease it again. Let's make it 30, okay? And run. So you can see that we have now sustained oscillations, okay? Sustained oscillations, as you can see here, okay? Now you can see that from here, after getting this sustained oscillations, I'm going to look for an important parameters. Number 1, K critical, the gain that led to this oscillation. The gain is 30. So our K critical is 30. Okay, so K critical, this value is 30. Okay, what about BCR? BCR is PU here, which is the period of this wave. Okay, so the period of this wave, how can I get it? If you double click here, I'm going to use a measurement like this, and then I'm going to zoom in here like this. Let's make it like this, okay? And then I'm going to drag this and look here for the peak value, okay? So you can see it goes down. So the peak at 1.898, okay? That is the peak. So I'm going to take number 2, come number 2 here, please, okay? 1.898, okay? So we get back like this. So this is almost the peak. So you can see that between 1 and 2, delta t, the difference between them, delta t is 2.55. That is the period. So our period is 2.55, okay? And our K critical is gain of 30, okay? Okay, so if you apply these two values to this equations here, you can get value of P and I and D. I already did this. I substitute with this K critical and PU or P critical and obtained P and I and D. So if I substitute it here and choose a PID controller, okay, what is your own gain? My own gain, as I calculated before, is 18, and the integral gain 1.275, and the derivative is equal to 0.31875. Okay, so these are the PID controller. Okay, now if you run this and look at the response of the system, this is the response of the system. Let's make it 30. Okay. Okay, so now it reaches the state of 1 after a longer time, and we have oscillations. Now I know that someone will say, hey, but it is much better when we used only a proportional gain. Well, you are not wrong actually. When we used only a proportional gain, we reached a better response. So it is not always, you don't need always a PID controller. Sometimes PI can be enough, or P can be enough, depending on how complicated or how non-linear is the system. Okay, so this is just how to apply this method, okay, regardless of it is giving a better response or a worse response. Okay, now what if you have another system like this one too, and you would like to get omega critical and the other value quickly, like K critical? How can you do this? You can do this using root locus. How you can do this? Just to get here, and let's say we would like to, number one, S, which is let's say G, which is our system, and this system I'm going to use another function ZBK, similar to the MATLAB Simulink, 0, poles, and gain. Okay, so we have 3 values, 1, 3. How many zeros you have? I don't have any zeros, so I will leave 2 brackets. What is your own gain? My own gain is 1. How many poles you have? Well, I have 3 poles. I have one at 0, one at -2, one at -3. So, and enter, so your G will be 1 over S, S plus 2, S plus 3. Okay. So we have this one, and I would like to know where is omega critical. So how can you do that? This is very easy. All you have to do is R locus and for G. So you are getting the root locus for G. Okay. And then go down here and look at this figure. Okay, these 2 lines are from the previous figure. Okay, so if you look carefully, that is the root locus for this system. And if you look carefully here, okay, if you go click here like this, you can see that if we drag it like this, okay, let's zoom in, okay, and then we need this point at exactly a gain of 30, which is K critical, same as what we get from the simulation when we changed the gain. And you'll find that the omega or frequency is 2.455, right? 2.45. So this is omega critical, and we know that PU is simply equal to 2 pi divided by omega critical. So let's do this. So we have 2 pi, which is 3.14, divided by omega critical, 2.45. So find 2.56, approximately close to 2.55, which we obtained from the graph. Okay, so this method is much easier without a trial and error, without changing this gain all the time and look at the response. Using the root locus, we found the solution directly. Okay, awesome. Now let's say I would like to see how can I do this, how can I apply a PID controller in this MATLAB code. Okay, so we have seen it in simulation when we have a feedback PID like this one, series with this one, and I would like to do a feedback to a step function. So you have G is our system, right? G equal to 1 over S, S plus 2, S plus 3. Now I would like to add the PID controller. So we have 18, 1.275 and this value. Okay, so I will keep it like this. So how can I do this? Let's say our compensator will be GC. Okay, so we will make it GC, referring to the compensator or the PID controller. In MATLAB we have a function called the PID, like this. What does it do? You can add proportional gain, integral and derivative. So the proportional is 18 if I remember, the integral gain 1.275 and the derivative gain is I already copied it like this. So this is our PID. If you click enter, you will see that GC, which is representing our PID controller, as you can see with the transfer function. So we have G and GC, right? So if I say open loop, open loop system like this, I can say open loop system is G multiplied by GC, right? So I will say equal to G multiplied by GC and enter. So you multiplied now these two transfer functions together. Now I would like to make a feedback, or I would like to make a closed loop system. So I will name it closed loop. Okay. And I would like make it closed loop. How you are going to do this? Using feedback, right? So in MATLAB we have a feedback and two brackets. What you would like to do a feedback for what? For this open loop system, right? For G multiplied by GC. I would like to make it a feedback, comma, with how much, what is in the feedback, just a unity feedback, right? 1 means a gain of 1 in the feedback. And then click on enter. You now have a overall transfer function for this system. G multiplied by GC and feedback, the overall transfer function after simplification will be this one. Now I would like to apply a step function. So I'm going to step, two brackets, and for the closed loop, okay, for the closed loop, okay, and enter. Let's look at the response. You can see this response, a step for the, like this one, okay. Now you will say that I didn't reach the steady state at 25 seconds. How can I make this simulation longer? All you have to do is that you can get back here, copy this line, step, and select what time you would like. Well, I would like it to simulate for 50 seconds. So I will click on type 50 and enter. You will now have a simulation for 50 seconds. Okay, so this is how you can apply open loop Ziegler Nichols method, the closed loop Ziegler Nichols method in MATLAB Simulink. And I hope you now understand how to apply this, or how to design using MATLAB Simulink, and how to program using the MATLAB code. Okay, thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy, or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You will find also in this academy, you will find the different feedbacks from some of our students that joined our courses. You can, for example, join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes and you can have them forever. And not only this, but any new course that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits. You will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics. Okay, and you will find that inside, when you join this membership, you will find this blueprint that will guide you in which classes you will start with when you join this membership. So thank you, and see you in our membership on Khadija Academy.